Good afternoon, everyone. I hope I am audible. Uh, just one quick check that I have started my recording or not. I guess it's recording. Yeah. So- Okay. So once again, welcome everyone to the first live interactive session of the course Fundamentals of Conduction and Radiation. Uh, this is a course that has been provided in NPTEL, and it is taught. I mean, it is uh, and it is co-taught by Professor Amaris Dalal from IIT Guwahati and Professor Dipankar Basu, also from IIT Guwahati. And I hope you might have received your, I guess it's the second assignment that you guys have received. And today it is basically the first interactive session of this course. And over here, this is me, Rajnandan from IIT Gandhinagar. So I am a Prime Minister Research Fellow from IIT Gandhinagar itself. And as a part of my teaching requirement, I get to take these live sessions in NPTEL. And I guess this is the second time I am taking this course. I took this course in the previous year as well, and we had some wonderful discussions and interactive sessions there, and I expect that we will continue to do the same, and you guys will basically like this session, and hopefully it will help you to subsequently solve the assignment problems and clarify your doubts uh, as and when you come across any difficulties or doubts across the courses and the week's contents that you get every week. Okay, so as I said, I put forward an quick, email in the discussion forum. So this session that we will, basically conduct every Saturday from 3 to 5 p.m. and this is the timing that we will always follow. And apart from this, if there are any changes in the timings, then you will be informed a priori through emails. But rest assured, if there is no emails and no information that you are provided, please be sure that we will meet on every Saturdays from 3 to 5 p.m. And the joining link for this session is the one that you got through your website, through the NPTEL website of this course. And we will use this link throughout the entire sessions for this course. There won't be any change in link. This is the one and only link. This is the one link that we will use throughout all the sessions. Okay. And few more, bookkeeping stuffs. So this being a live session, you are always welcome to join this session, and you are even, it's not just a welcome, you are encouraged to join this session because it will inevitably, help you immensely to solve the assignments, because as and when because the theory classes or the videos, these are recorded, okay, and you don't get to interact through these videos because those are past recordings that are played that are currently being uploaded on the website. But in this session, it is when it is that time where you get to interact one on one, okay, through with me or whosoever is the TA of this course. And for this course, I'm the only one who will be taking this live session. So basically, we get to interact, and it helps us, not only me but the entire team of this course, to basically understand where you are, you are stuck, or you're finding some problems to understand. And to understand the stuffs that are being shown every week, or you're having some difficulty somewhere else in the context of the course. So this is where we get to understand, and this is where we can actually try and solve these queries that might arise that might arise at your end. Okay, so having said that, that's the only that's the sole purpose of this interactive session. And we expect that you will participate, because yeah, we as human beings, it is not possible that you can understand everything once by just looking or browsing the video, by browsing the lecture videos just once a week, because that is not possible at any level of a human, because you will inevitably come across certain things which you will not understand in the first glance, or you will not understand in the week's contents. And this is primarily the place where you come, and you I mean, get clarified. You get things clarified. Okay. So, please participate. But we understand that the audience here is a broad, it's a broad spectrum. So this video or this session is recorded and it will be uploaded along with the notes that I will write here. So all these notes that I will write here and the video of the session there. So this session itself will be recorded and it will be uploaded into the course website, and you will separately get a link in the website where the uploadings and the class notes of this session will be provided to you. And if you miss any session because of certain difficulties, which is understandable, you can always access that links and the notes which will be provided in the website. Uh, the link will be shared to you very shortly. I mean, that will be shared from the NPTEL team, but you will see in the website that there is a link against every week's for the week's live sessions and the class notes that I will primarily write when I take these sessions. Okay. Lastly, what I want to emphasize is that please actively participate in the discussion forum of the course. This helps us to stay connected, because this is not a one way thing that I or any of the team members just come and give some problems and solve some problems and then it's done. It's not like that. It's a two-way thing where we also need to understand that are you being able to get the things that we are trying to say or not. Okay, so yes, the number one thing is that join the discussion forum. I mean, join this live session to be to interact with us and to clarify your doubts. Apart from that, apart from this 3 to 5 window every week, in any point throughout the week, if you feel that you need some things to be addressed, please use the discussion forum and we will make sure that your query gets clarified. Me or any one of the team members of this course will make sure that your query gets clarified in the discussion forum. So please actively participate there. And this is also, it also I mean, it also helps us as a metric to basically see how much things are being clarified, things are getting clarified at your end. Okay, so that's the I mean, what to say, the bookkeeping that I was intending to say. So now what we will do is we will start off by this week's contents. I mean, that's the first week's contents. In this week, it's just an introduction. As you know, this just an so this course is primarily so in this course we'll primarily focus on conduction and radiation. But in this session, I mean, or in this week, or in the assignment that you guys just, I mean, you guys are supposed to submit it. Yeah, I think it's by 2nd of September, or I mean 2nd of August, or I forgot the due date, but it's in I mean, it's nearer to 2nd or 3rd August. Okay, but anyways, that's the first assignment that you're going to solve. And today, in this week's contents, we will discuss problems similar to the ones that you basically saw in the first assignment. Okay, now, having said that, we will not exactly, or I will not exactly solve the problems that are there in the assignment, because then we lose the spirit of solving the assignment, right? Because that is for you to solve. I cannot just solve exactly the sum that is there in the assignment, where I'll just solve for the answer and you will just write the answer in the submission sheet that you are given, so that it doesn't serve the purpose of your learning, right? So what I will do is, we will not exactly solve the problem that is there in the assignment, but what I will make sure is, we will I have picked certain problems that are in line with the problems that are there in the assignments. Okay, that are similar but not exactly same to the ones that we will be solving for assignment 1, and all the subsequent assignment will follow the same. So the analogy is just the same for all the other submissions of the assignments. Okay, so in that spirit, what will happen is that you will understand how to basically tackle the problems you are given in the assignment, plus the problems which we will solve it in the discussion forum. These are a one step high. So you can say these are a one level higher problems to the problems that are there in the assignments. So solving these problems in this class will not only help you to solve the problems in the assignments, but also your understanding will get clarified. Okay, it will be enhanced basically. Okay, and that's the idea behind how I choose the problem that we will be solving in the in the week's contents. Okay, week, I mean, meaning in these live sessions. Okay, so that's the idea. And lastly, a brief introduction of myself. As I said, I'm a PhD scholar and a PMRF fellow from IIT Gandhinagar. I work in the area of fluid mechanics and in particular microfluidics, where I deal with something which is called electrophoresis, where I try to see how charged particles move in fluids in the presence of electric fields. And this and this is the broad area of my research. You can uh, you can if you are interested in the work that we are currently doing here at IIT Gandhinagar, you can always look into our websites. You can search my name, or you can just look into the general website of IIT Gandhinagar, to if you are interested in you know in taking up these kind of research problems in your career ahead. Okay, so that's a brief introduction from my end. So let's take a 2 minutes pause. And as I said, just a final thing that I want to convey is that although this session is for 2 hours, it is not a hard and a fast rule that we will always stretch this session for 2 hours. It is like we will see how much we can take, we can basically take each day. If you feel, or if I feel that we are basically stretching too much, then you can always call it a day, and we will carry up from the next day onwards. Okay, we'll just concentrate on the learning and not on the time stamp that we are given. That's a time slot that we have. But it is not always necessary that all the sessions will always be of 2 hours. Sometimes it may go up to 2 hours, depending on the learnings that we will see. And sometimes, like, if I feel that there is too much in your plate, then we can always stop at that point of time, and we will carry forward from the next session onwards. Okay, so the main objective, in a nutshell, the main objective is learning, and we will make sure that you learn the best. So you basically learn in the best possible way that you can. Okay, so that's the brief idea. That's the overall goal of this session. I'll stop here for a couple of minutes. In all the subsequent session and in this session, you will see that we will take momentary breaks. This will recharge you, of course, and then you can always ask doubts at any point of time in those breaks, or you can also ask as and when a doubt arises in your end. Okay, at your end, basically. So we'll stop here for a couple of minutes, and then we will start off with the week's contents. And as you can see from the screen, in this week, and also in the week one of your lecture classes, the main topics of interest was just a preliminary introduction to conduction, convection, and radiation. And although this course primarily deals in conduction and radiation, but as an introduction, because these three modes of heat transfer are generally are generally studied together, we will also deal I mean we'll also briefly look into something which is known as convection. And we will also see that what convection does essentially mean. Can convection occur uh, without conduction, or like how these modes of heat transfer interact with each other, and what basically is radiation. Does radiation occur independently, or they are linked to conduction and convection? And we will see all these things today, because this is an introduction to these three aspects of heat transfer. And based on this, as I said, the focus will be all problem solving, and through problems we will see this how this theory builds. And then we will basically see how these modes of heat transfer come into the play. Okay, so that's the agenda for today. And what I will do now is I will put forward the first problem. So you can see it from the screen that this is one problem that we'll solve. I'll not discuss the problem. I'll pause for around 1 or 2 minutes, and then I'll let you to basically see the problem, and then I will take it up from there. Okay. All right. So let's get into the business. So so since this is the first class, we'll proceed very slowly. It's a very fundamental problem. In fact, all the problems that we will see today, these are very fundamental problems related to conduction, convection, and radiation. And you have solved this kind of problems in the theory class as well. And these kind of similar problems are there in your assignment as well. So please pay attention to the details that we will discuss here and in all the forthcoming problems. And we will, as I said, we'll proceed very slowly, and as and when you find any difficulties, please feel free to let us or let me know. Okay, so what we are given is we are given a slab, as you can see in the screen, and this slab has a length L, the width is W, and the height of the slab is given as H. So this you know gives us the entire dimension of the slab, and it says that, so the question gives us a hint that the length of the slab is very much less when compared to the width and the height. Okay, this is the first information that that the question is saying us, that L is of the order of, I mean, it's so the order of the length of the slab is very much less than the order of the width and the height. Okay, having said that, what the problem statement says to us is one end of the slab, indicated by this red line that I just drew, it is exposed to a temperature of T1. Okay, now this is where you need to pay some attention. Although it might appear simple, when I say that one face of the slab is exposed, or one end of the slab is exposed to a temperature T1, I am essentially indicating that the entire face that I have highlighted here, this entire face is at temperature T1. I hope you try to I mean, I hope you understand what I am trying to say here. So I'll repeat what I mean is that when I move, so let's first understand this by drawing the coordinate system of this case. Okay, so this are the Cartesian coordinates that that we will use. As I said, this direction we'll call it as x, this is y, and this turn out to be z. So when I say that my face is at temperature T1, this means if I move along this face in the y and in the z direction, I will see the same temperature T1. That is, the temperature does not change when I move in the y and in the z direction of the slab. Okay? Now you may ask me, why is that case? That is not a physically, because physically if you take a slab and you expose a face of a slab to a particular temperature, and right now I'm not interested in how that face is being exposed to a particular temperature. I'm assuming that there is a slab and its face is at a temperature T1, but physically you can argue that the face will not always be maintained at the temperature T1. There will be some patches where temperature will be T1, there will be some other patches where temperature will be less than T1. Okay, on and vice versa, basically, depending on what source of heat that you are using. Now, that's the reality. But if we consider that, if we so there is something which is known as one-dimensional heat transfer approximation. So in the approximated scenario where I consider that my heat transfer is one-dimensional, I can assume that the slab which is of our interest, this is exposed to a uniform temperature T1. That is, the only possible way that temperature can vary is in the x direction. Okay, that's an assumption that we are invoking, basically. So this is the first thing that we will understand. So you're assuming, as I said, so you're assuming that my heat transfer is one dimensional. So now this as I said, this is an assumption. This is not a realistic thing that we are trying to put forward. Yes, it might happen sometimes in reality based on certain circumstances, but in this context of the problem, we are assuming that my heat transfer is going to take place only in the x direction. Now, since heat transfer is taking place only in the x direction, if you move along the y and in the z direction, you will see the same temperature, because we are just assuming that my heat transfer is one dimensional only. So now, if you ask me, can because see, just by solving a problem on pen and paper, and if it doesn't have any connection in reality, then it's of no use, right? Because if reality says something else and you are just assuming something and solving it on pen and paper, and you are getting some result, that's fine. But if you cannot connect into the realistic scenarios, then it doesn't, bring anything of any physical importance. Okay, so now let us try to understand then that how this assumption of 1D heat transfer, you know is reflected in reality. So in reality, what happens is, if you consider this dimension, that is the dimension in the x direction, to be very much less than the dimension in the y direction, then your approximation of one dimensional heat transfer, that is your heat transfer being taking place only in the x direction, holds good. The reason behind this can be understood from the fact that if this dimension is small and you are maintaining these two phases, on two different temperature nodes, then the gradient has to be large, because your prescribed dimension is small. So if your gradient is large because of the fact that your phases are at different temperature, with let's say T1 and T2, and in the direction of heat transfer your length basically which says is less, okay, then the approximation of one dimensional heat transfer is says that it's then I would say it in the other way around. Then I would say that one dimensional heat transfer approximation, give us, a fair amount of accuracy in this scenario. Okay, so so then so the idea that I want to convey is that yes, the heat transfer is one dimensional, and this is a good approximation. So I would say this is a good approximation, since my length, okay, which so this length is critical, because this length, it is along this length only there are two phases which are maintained at two different temperatures. Okay, so since this length is very much less than, the other dimension, which is width comma, which is the width and height, the one dimensional approximation will give you a fair, so it will give you mostly an accurate results to any other, to a general idea where you are considering actually a two dimensional or a three dimensional heat transfer problem. Okay, so so that's that's the idea. So if someone asks you that under what scenario is one dimensional heat transfer assumption valid, so this is exactly the scenario. Okay, so if you have a slab, in reality, if you have a slab and you are maintaining the faces of the slab at two different temperature, and the gap between these faces, if it is very much less than the other dimension, than the other, permitted dimensions of the slab, then a one dimensional heat transfer approximation will give you a fair, a fair analysis. Okay, in reality, I would say. All right, so that's the assumption that we'll use in this problem. I hope this assumption and the context of the problem is clear to you. Okay, so once we understand this assumption, now we'll get into the fact that what the question is asking us. Now at least we know that my heat transfer is one dimensional, and I know that it is in the x direction. Now if you ask me why this is the case, because there is a temperature gradient that is in the x direction, because the left, I would say the left face is maintained at temperature T1 and the right face is maintained at temperature T2. So since there is a gradient in temperature in the x direction, I basically, so since there is a gradient in temperature in the x direction, there will be a heat transfer that will take place in the x direction. Okay, so having said that, now we will see the first quantity that we are asked to evaluate, which is the heat flux. Okay, so based on this 1D, one dimensional heat transfer, the heat flux that we will evaluate, and we will denote the heat flux as Q double prime. So whenever I say there is a quantity which is double prime, okay, it means that it is flux, and flux is the so if I say heat flux, it is rate of heat transfer per unit area. So if I calculate something per unit area, I will always denote it by a double prime. If I calculate something per unit length, I will denote it by a single prime. If I calculate something per unit volume, I will always denote it by a triple prime. Okay, this is the nomenclature we will follow throughout this course, because we will need these three quantities: heat transfer per unit area, heat transfer per unit length, and heat transfer per unit volume. And if it is just heat transfer, we will just say it is Q. Okay, I hope you are with me on this so far. Okay, so now since they are asking us to calculate flux, we will basically calculate Q double prime. But here is the scenario. In general, as you have seen in the lecture series, heat flux is essentially a vector. It is not a scalar quantity in general. So if I say I am dealing with a vector, because they are asking me to calculate the heat flux, and I know that heat flux is a vector. So I will denote any vector by a dash sign. Okay. There is also a higher dimensional, and it's not higher dimensional, I would say there is also a quantity which is called tensor. And I know you guys, mostly the audience of this course is not so familiar with the word tensor, but in brief or in a nutshell, I would say that tensors are any quantity whose, you know, I mean, that so if a quantity not only depends on the direction but also depends on the orientation, okay, if that physical quantity shows this kind of dependence, then it's called as a tensor. For example, vectors only show dependency on directions. Okay, tensors on the other hand will depend on direction as well as the orientation. Okay, that's the basic difference between a vector and a tensor. And in fact, a vector is called as a rank 1 tensor. Tensor is a more general thing. A vector is called as a rank 1 tensor. A scalar which doesn't show dependencies on direction as well as on the orientation, they are actually known as zeroth order tensor, which is just a scalar. Okay, so taking this background information, heat flux, as you have seen in the lecture series, is a vector because your flux actually depends on which direction you are looking at. So if it's a vector, I will always denote it by an undersign. If it's a scalar, there won't be any undersign. Okay, so the most general, I would say, law, as you guys might have got a flavor it in the theory classes, the most general law which connects heat flux to temperature is known as the Fourier law. Okay, the Fourier law of heat conduction. And it says the most general form of Fourier's law says that your heat flux, which is a vector, is equal to your thermal conductivity, which essentially is a tensor in general, times your gradient in temperature. Okay, and this gradient in temperature is in most general sense, it's a vector, and the thermal conductivity is essentially a tensor. So what you are doing actually is the right hand side says that you are multiplying a tensor with a vector. Your vector is your gradient in temperature. This means it says how much your temperature is varying along a particular direction. This is precisely what the gradient in temperature says. And your thermal conductivity, which we will denote as by K, this is in general a tensor. But this, this statement that I have written here, that your heat flux, okay, is equal to the thermal conductivity times gradient in temperature. This is the most general form of Fourier's law. Okay. See, we are all trying to understand this because the question has asked us to find out the heat flux, and this is the only way how you can calculate heat flux. Okay, so this is known as the general form of Fourier's law of heat conduction. Okay, but assuming that your thermal conductivity is constant, okay, so now we'll invoke one more assumption. So we'll invoke that your K, which is thermal conductivity, this is constant, and it is not varying along the x and not varying along the y. So you can show that. I will not show the mathematics here. If you are interested, you can ask me separately and I will show you how exactly this comes. But you can show that under the assumption of 1D heat transfer and if you assume that your thermal conductivity is constant, your heat flux in the x direction, because we are precisely trying to calculate it in the x direction, is equal to K times dt dx. That's it. Okay. So this is not, so please try to understand that this is not the general Fourier law, but this is a consequence of the general Fourier's law, which which says that under the assumption of 1D heat transfer, and if you assume that your thermal conductivity is constant, you can basically show that your heat flux in the x direction. See, now this becomes a component of a vector, and that's why I have removed this dash sign, because we are only interested in heat transfer taking place in x direction only. It says that it is k times dt dx. That's it. Okay. I hope you are with me on this so far. I'll stop here for a couple of minutes. If you have any doubts, you can ask me, or any suggestions are welcome. Okay. So let's do a quick recap. So what I say is that we were asked to find out the heat flux, and the only way of obtaining heat flux in conduction is by using, because see, this is a conduction problem, as we all know, because it's a slab which is stationary, uh, and they're asking us to calculate the heat flux, meaning that I have to use something which is known as the Fourier law, and you have already seen that you have already seen the discussion of Fourier's law in your lecture classes. So this is precisely the most general form of Fourier law, but since the question says that we can now invoke the assumption of 1D heat transfer and the thermal conductivity being constant, we can say that heat flux now becomes k times dt dx. Okay, so that's it. Since you know the value of k, okay, your K is given to be equal to 0.29, and remember the unit of thermal conductivity is watt per meter Kelvin, and you know that the temperature difference is 10 degrees Celsius between these phases T1 and T2. Okay, you can now you can now say that your Qx is K times T1 minus T2 by delta x, where delta x is nothing but the length that we are considering. All right. Now, here is something that again you need to understand. Although it appears very simple, what I did is I have represented this dt dx, which is the gradient along the x direction of the temperature profile, as a linear profile, because I have just calculated the difference of the temperature between the phases divided by the length. So what I am essentially doing is I am approximating, okay, so please try to understand. I am saying that under the consequences of 1D heat transfer and your thermal conductivity being constant, I am saying that your temperature profile varies linearly between these two phases. Okay. So if your temperature profile is linear, which is a consequence of 1D heat transfer and your thermal conductivity being constant, I can say that my dt dx will just be T1 minus T2 divided by delta x. Okay. This, again, I would say, I would like to clarify that so this is your temperature node T1 and this is your temperature node T2, because since T2 is less than T1, this is precisely how the temperature profile would look like. But the important point to understand is that since you are assuming that your heat transfer is one dimensional and you are assuming that your thermal conductivity is constant, you are saying that the slope of the temperature, which is dt dx, the slope of your temperature profile is a linear, so the slope is linear, meaning that the slope is, the temperature distribution is linear, meaning that the slope is going to be constant, is equal to your T1 minus T2 divided by delta x. So this is again a consequence of your linear of the heat transfer being one dimensional and the thermal conductivity being constant. Okay, and this directly comes from the Fourier's law itself, if you pay a close attention to the Fourier law. Okay, so I repeat, and you can also verify that if your temperature varies linearly, then your slope, which is the first derivative of temperature, has to be constant, and this is precisely what you are writing here. Okay, and that's the reason why I can write dt dx as T1 minus T2 by L. So now that's it. Now it's just a value substitution. So you just need to substitute the values. Your K is 0.029. This is the most easy stuff of the problem. just need to substitute the values T1 minus T2. That is, they are saying that the difference in temperature between these two phases is equal to 10 degrees Celsius. So it just become, 10 divided by your length. Your length is 20 mm, and you need to convert it into SI units. So this becomes what? This becomes 0.02, if I'm not wrong. And if you carry out, if you carry out this math, which is just this multiplication, 0.29 times 10 divided by 0.02, you will see that your flux will come out to be 14.5 watt per meter square. Just put this value in your calculator and just check it out. Your flux will be 14.5 watt per meter square. That's it. So that's the answer. So if you are just naively do this problem without understanding much on the assumptions that we saw, much on concentrating on why your slope is basically linear, it's just a simple math, right? Just blindly apply Fourier's law. I mean heat transfer flux or rate of heat transfer per unit area is k times dt dx, and then just substitute the value. It appears very simple, but you can see that in this mere simple formula there is a lot of things that basically come into the picture if you pay a closer look into the problem. And I repeat, one, how basically you get this form of Fourier's law from the generalized concept of Fourier's law. Okay, and quickly, since this is an introduction, this is an introduction, I will quickly discuss, because I feel this needs to be discussed. I will quickly show you how you get this from the most general form of Fourier law. Okay, so it's okay if you don't completely understand it. This is understandable, because since I expect that most of the audience of this course is in the undergraduate level of their courses, you might not be exposed to tensor algebra and things like that, but I feel a little bit a little glance of this would it won't cause any harm to anyone. Okay, so I'll quickly show you how you basically get this form of the Fourier's law, which is the simplified form of Fourier's law, which you guys always use, from the most generalized form of Fourier law. Okay, so what you can do is you can always write, so as I said, my heat flux in the most general form is equal to the thermal conductivity tensor times gradient of temperature. You can actually show that so a multiplication, see this, so this is a tensor, you are multiplying with the vector. This is known as contraction. Actually this multiplication in the language of tensor algebra, this is known as contraction. Okay, so you can show that whenever you you can show that if a tensor is multiplied with a vector, a tensor which is of rank 2, a vector which is of rank 1, when you multiply them, you will get a vector of rank 1. And that's the reason why your flux, which is a vector, it is called as a rank 1 tensor basically. So you can show that whenever this contraction is carried out, since thermal conductivity being a tensor, it has components like something like this: kxx, kyy, kzz. See, because it's a tensor, it has two indices. So you guys might have seen that a tensor, let's say I'm talking about the tensor alpha, it has two indices, and it is generally represented as alpha ij. One of these indices talks about, so the first indices says about the plane. Okay, this I says about the plane on which you are basically seeking to get the value of the tensor. The second in this talks about the direction. Okay, that's how you represent tensor. So when I say kzz, for instance, I am saying that what is the value of the thermal conductivity on the z plane and in the z direction. Okay, that's typically how you identify tensors. Okay, so that is kxx, kyy. Sorry, I wrote it in a different. Sorry, very sorry. This is actually kxy, and this is actually kxj. So there is something which is known as Einstein's summation rule, and that's the reason why you write these terms as kxx and kyy. Okay, uh, we'll not go into details of this. I am just showing you how do you basically get the simplified form of Fourier's law. Okay, if you are interested, you can ask me and I'll be happy to explain why how you write tensors like this. Okay, let me first finish this matrix. So it comes as kxy, because actually this is kyx, but you can show that your thermal conductivity is a symmetric tensor. I think it's a symmetric tensor, but anyways, we won't require that information much here. So this becomes kyz, this is kyy, Zx is k zy, this is k zz. Okay, so that's how you represent this thermal conductivity in tensor form. Okay, now there is something which is known as a symmetric tensor. As I would say, if your tensor is symmetric, you can show that your kyx is equal to kxy, and similarly you can show that this is basically equal to this is basically equal to this. Okay, that's so this is known as symmetric. So they are a special class of tensor which are known as symmetric tensor. But anyways, so this is how you represent a tensor in a matrix form basically. And then what you are doing is you are representing this vector grad of t. So this grad of t would appear as so since grad of t is a vector, your tensor is a 3 cross 3 matrix. Your vector would just be a 3 cross 1 because this is just a vector. It is only dependent on direction. Okay, so your grad of t will be del t by del x, del t by del y, and del t by del z. Okay, so now if you want to write your heat flux vector, okay, it would basically be, so you just need to carry out this matrix multiplication. Okay, that's it. So your first term would basically be kxx del t by del x plus kxy del t by del y plus kxz del t by del z. This is your first term in the x direction. Okay, and similarly you can show that your y direction, you just need to do this matrix multiplication. It will just be kxy del t by del x, yeah, it will be kyy del t by del y plus kyz del t by del z times ez. Okay, please bear with me. You don't need to, at this point of time, you don't need to be very much, worried about how all these things come. I'm just showing you a flavor because I mean, we will not do this kind of exercise in the next class, from the next session onward. This is just a flavor of actually how the math works, and you will appreciate that, okay, there is an intrinsic, there is an intrinsic complexity that always lies whenever we are using some simple formulas, because these simple formulas doesn't come, so they are just not ad hoc. They comes from certain assumptions, certain approximations, and this is just one flavor that I'm giving you, how that simple form of Fourier's law k, that heat flux equal to k times dt dx, comes from the generalized concept of Fourier's law. Okay, so it's okay if you don't understand this in your first instance, but I'm just showing you an example. Okay, so in the z direction, so remember this ex ey, these are unit vectors in the x and y, x y, and similarly in the z direction it would be k zx del t by del x plus k zy del t by del y plus k zz del t by del z ez. Okay, all right, now you can basically argue that since we are assuming heat transfer only taking place in the x direction, that means the component of flux in the y and in the z direction, all these components has to be equal to 0, because we are just assuming that your heat transfer is one dimensional, which means the component of flux in the, in the y direction and the component of flux in the z direction should be 0. Secondly, you can also say that since your heat transfer is one dimensional, you can hold on, did I make any mistake? I guess I'm not. Okay, no, it's fine. It's so this is perfectly fine. The multiplication is perfectly fine. All right. So you can further show that since you just have a temperature gradient in the x direction, this means your gradient in the y direction is 0, your gradient in the z direction 0, which means you just end up getting, so what do you get? So if you just put all these terms to be equal to 0, you just end up getting your flux as kxx times del t by del x ex. Okay, and I'll remove this unit vector by just saying that instead of writing it as a vector, I'll say that its component, which is just the x component, is kxx. I can say that del t del x will transform into dt dx because your temperature is just a function of x. Since your temperature is just a function of x only. And then I will say that since my thermal conductivity K is constant, I can say that my xx component is just a constant K, which is just a constant. And this is how, after all this simplification, you get the familiar form of the Fourier law that you guys had been using throughout this class. But at least now you can understand the complexity that builds in whenever you try to see things a little bit closer and see things a little bit in details. So from this general Fourier law, at least now you can say that how, by invoking the assumptions, okay, you have reached to this generalized, to this simplified form of Fourier's law which you guys had been using so far. And that is exactly what we basically did here. Okay, and then just substituted the values and got the form, got the value of heat flux. All right. So again, I say so whatever we did here, it is, it's phenomenal if you just understood it. If not, please don't get worried. These are the things that you will again learn in your higher classes when you basically learn something which is known as tensor analysis and vector analysis and things like that. Okay. All right. Anyways, we are not done yet in this problem. They have also asked us to evaluate one more thing, which is known as the rate of heat transfer. That is easy because the flux says that it is rate of heat transfer per unit area. So in order to find out the rate of heat transfer, you just need to use the flux multiplied by the area which is in the direction of heat transfer. So since we know that my heat transfer is taking place in the x direction, the area which is in the direction of heat transfer will be in the yz plane, which is nothing but the area of the faces of the slabs. And since the slab is uniform, you calculate the area of this face or you calculate the area of the inner face. It is just the same, and they have said that the area is 4 meters square. So what you need to do is, that's easy, right? What you need to do is your rate of heat transfer. Since rate of heat transfer is just watt, we will denote it as by qx, and this is your heat flux, which is qx double prime, which is rate of heat transfer per unit area multiplied by your area. But remember, you need to understand that this area is always perpendicular to the direction of heat transfer. Okay, and then you just substitute the values. You got your flux as how much? 14.5 watt per meter squared multiplied by the area. I think the area is 4 meters squared. If you do this multiplication, you will see that I think you'll get around what, 58, maybe 58 watt. Okay, that's the value of your rate of heat transfer. Okay, that's it. We have finished the first problem, and these two are the results that they've asked us. All right, guys. If any questions, you can ask. I'll stop here for a couple of minutes before starting the next problem. In the meantime, if you have any questions, you can ask, or if, as I say, if there are any questions that you feel that arises when you do revision of these things and when you look into the week's contents, always feel free to post that in the discussion forum, and we'll make sure that we will get back to you as and when you post these questions from your end. Okay. All right. So far, I hope you understood this. Again, I repeat, this analysis that I did, that I have multiplied a tensor with a vector which is gradient of t. You might be surprised, or you might be questioning yourself that these things is not clear. How did I write a tensor in this form? These things will be clear to you when you take some more higher courses on tensors. But as of now, I'm just trying to give you a flavor that how you get this this simplified form of Fourier's law from the most generalized Fourier's law, which is basically this. Okay. All right. If there are no questions, we will solve the second problem. The second problem is also a bit similar. Now we know we'll not go into those in-depth analysis of Fourier's law, the general form and all, because I have showed that in one problem. Because since in this course mostly as in when until and unless I say that the assumption of one-dimensional heat transfer is not valid, we will assume that heat transfer is just one-dimensional, and except from one topic, they so I think, yeah, except from one topic, in all the other topics that we will follow, we'll assume that my heat transfer is one dimensional only. Okay, and rest assured that if your heat transfer is one dimensional, you can use your simplified version of Fourier's law, which is, and of course if the thermal conductivity is constant, you can say that your Fourier's law is just q equal to k times of dt dx. That's it. Okay. All right. So so the second problem is very similar to the first problem, as you have seen from your screen. So what they have said that we have two cases. One, a single glass pane, which of which the faces are maintained at two different temperatures, T1 and T2. T1 is 15 degrees, T2 is minus 20 degrees. And again, they have said that the length is so small that the one dimensional heat transfer approximation holds good, and we'll assume that the rate of heat transfer is in the x direction only, what we have assumed it in the previous problem. And based on this, and given that this length is 5 mm, your width, this width and this height is given to be equal to 1 and 2 meter, with the thermal conductivity of glass to be around 1.4 watt per meter Kelvin. They have asked us to calculate what will be the heat transfer in this scenario, and in a second scenario where now they have used an airspace maintained at two temperatures T1 and T2, which is of course different to the temperatures that we saw here, but these are two different temperatures. And what they have asked us that if now there is an airspace in between these two glass panes, they say to us that the phase temperature of this airspace is given to us, which is T1 and T2, and given that air has a thermal conductivity of this much with a length of 10 mm, taking into consideration that in this scenario also heat transfer is taking place in the x direction, they have asked us to calculate what is the rate of heat transfer in this second scenario. And a qualitative, we will see that there is a huge difference, at least quantitatively, when you compare the rate of heat transfer in this first case and to the rate of heat transfer in this second case. And we will argue that this huge quantitative difference between the two rates of heat transfer, whenever we are including an airspace is in between these two glass panes, is attributed to the fact that air has very low thermal conductivity. Okay, that we will see very shortly. And we will do a very interesting problems where we will try to analyze the heat transfer analysis of airplane windows. Okay, that we will not do today. We will do that whenever we learn something which is known as resistances of, they are basically known as resistance networks of conduction heat transfer. When we learn that aspect, we will see that we will then learn something which is known as heat transfer analysis in airplane windows. And then we will see that how air spaces in between airplane windows play a huge role in minimizing the heat loss from the airplanes heat loss inside the airplane's body to the ambient, which is at a much colder temperature than the temperature which is inside the airplane space. Okay, that we will see basically, but that's not what we will do today. In fact, what we will do in this problem is, it's a simple case. In one case we just have a glass pane maintained at two different temperatures, everything else is given. Calculate the rate of heat transfer On the second case, we'll pick an airspace in between these two glass panes. The glass panes doesn't become these glass panes, doesn't become the calculation of heat transfer in this glass pane in the second case is not necessary, because they have itself given us the temperature of the airspace, basically. That is the space, the faces inside the glass pane, which is exposed to the airspace inside. Okay. In that scenario, we will see what is the rate of heat transfer in this case, and then we'll compare these two rates of heat transfer. That's the idea that's the thing that we will try to evaluate in this second problem. Okay. I'll stop here once again for a couple of minutes. If you have any questions, you can ask, and I'll be happy to, you know, answer them. All right. So let's get started. So for the first case, we'll call it as case A. We will simply use, so now we have the Fourier's law, the simplified version of the Fourier's law at our disposal. Because I'll not write it repeatedly, we are assuming that thermal conductivity is constant. That is, the thermal conductivity of glass is not a function of space. That is, it is not a function of the coordinates, the local coordinates in fact, and it is not a function of temperature either. So thermal conductivity is constant, and we are assuming that heat transfer is one dimensional. And the argument, as I said, we put forward that this length is very much less than the width and the height of the the plate or the pane, basically. And in that context, the one dimensional heat transfer is essentially valid, and we will use these assumptions. So the assumption of one dimensional heat transfer and constant thermal conductivity enables us to use the simplified form of Fourier's law, which is nothing but your heat flux in the x direction to be k times dt dx. Okay. And under the scenario that it's a one dimensional constant thermal conductivity case, you can say that your dt dx is going to be, so the slope of your temperature is going to be constant, meaning that your temperature is going to be linear, is something that we already saw in the last problem. And then you can say that your dt dx is equal to your kg, which is, so this is going to be kg because this is the thermal conductivity of glass, times T1 minus T2 divided by L. Okay. So if you evaluate this heat flux, kg is 1.4 times of T1 minus T2. T1 is 15 degrees Celsius, T2 is minus 20. So this becomes 15 plus 20 divided by L, which is 5 mm. So this becomes 5 into 10 to the power minus 3. And if you do this calculation, you can show that. Okay, so this is your flux, but they are not. So this is going to be watt per meter squared. So the rate of heat transfer is nothing but this flux times the area, which is perpendicular to the direction of heat transfer, as I said. And they have said that your area is nothing but your width times the height, which is just 2 meters square, because the width and the height is given. So this is going to be your flux, which is this 1.4 into 15 plus 20 by 5 into 10 to the power minus 3 times the area, which is 2 meters squared, and this is going to be your rate of heat transfer. And if you calculate this, your rate of heat transfer in the first case, we'll call it as Qx of A, you will get it to be around 19600 watt. Okay, that's simple. Just use the simplified form of Fourier's law, multiply it with the area perpendicular to the direction of heat transfer, and you get the rate of heat transfer. That's it. Okay, so that's the rate of heat transfer for case A when there is just a single glass pane. Now we'll follow the same analogy and calculate the rate of heat transfer for this airspace. That is simple. It will just be k times of air times dt dx. You know dt dx because you know the temperature of these two faces, with its length. You know that, you know what is Ka. Let's just calculate the rate of heat transfer. That's it. So the rate of heat transfer for case B is going to be Qx of B. This is going to be K for air times dT dx times the area. And this would be in watt. Okay. And your Ka is given to be equal to 0.024. Your dT dx would be what? So your temperatures on these faces are 10 and minus 15. So this would be 10 plus 15 because there is already a minus sign. So it's going to be 10 plus 15 with length. How much is the length? So the length is 10 mm. So this length is 10 mm. So this is 10 plus 15 by 10. Multiply it by the area. So the area is just 2 only because the width and the height is just the same for both cases. And if you do this calculation, you will see that your heat transfer rate for this case, which is Qx of B, is 20 watt. Okay. So you can see this. So there is a huge difference with respect to the heat transfer rates of case A and case B. One is what? 19600 watt, which is roughly around 20 kilowatt, and the other is just, you know, 0.1 kilowatt. That's it. 20 kilowatt and 0.1 kilowatt. There is an order of magnitude difference of 10. Okay, sorry, not 10. It's so roughly so roughly, you know, this is 100 times. This is 100 times, you know, larger than this basically. Okay, so just by putting air in between, what you saw that the rate of heat transfer has decreased by 100 times. And that is typically the reason why airplane windows have you know, a space in between their glass panes, and that space is filled by then and that space is just vacuum. That's it. And vacuum means it's just, you know, air molecules which are not moving. It's just like that. And that's the reason why, in order to minimize the heat loss from the airplanes fuselage to the ambient air, they have air spaces in between the glass panes. And next time you board an airplane, please take a close look and you will see that there is essentially air spaces. Now this is just a very simple problem that we did. When we'll be learning something which is known as resistance analysis in heat transfer, we will, you know, we will see that how by, you know, putting in air spaces in between glass panes increases the resistance to heat transfer, and it minimizes basically the rate of heat transfer. And that we will do thoroughly when we learn the concepts of resistance network in heat transfer. I think that we will do it in week 3 or week 4. Uh, but yeah, then we'll come back to this problem and we will solve a real life problem of aeroplane windows. And then we will see that yes, indeed, if you put in glass spaces, the rate of heat transfer decreases significantly. Okay. All right. That's it. That's the second problem. I hope you liked it. If you liked it, I'll stop here once again for a couple of minutes. Then we'll solve another problem. Once again, it's a simple problem. Uh, you can browse this problem, and if you have any doubt, you can ask me, and I'll be happy to clarify this. Okay. All right. So we will look into a third problem, which is again a very simpler and a similar problem to the ones that we just now solved. It says that heat flux through a wooden slab or a wood slab of this much thickness, whose inner and outer surface temperatures are 40 and 20 respectively, is determined to be 40 watt per meter square. What is the thermal conductivity of wood? That's what they're asking. It's a very simple problem. Apply Fourier's law. Now that they in the earlier two problems we calculated the flux. In this problem, they have said that the flux is given. You need to calculate the thermal conductivity. But again, you need to be very careful in writing that simplified form of Fourier's law, because you need to consider that your heat transfer is one dimensional and your thermal conductivity is constant. And under these two scenarios only, as I have seen, as we have saw repeatedly, you can say that your heat transfer rate now will, since they have given us the area, okay, because I guess they have given us the area, yeah. Oh no, they have just given us the flux. So you can just use the Fourier's law, which says that your flux, let's say Q double prime, is equal to your K times dt dx, which is nothing but the simplified Fourier's law as we have seen repeatedly. And they have said that your flux is 40 watt per meter square. K is something that we will find out. Dt we can calculate because it is just going to be 40 minus 20, okay, divided by the thickness, which is 50, which I will write it as 50 into 10 to the power minus 3, okay. And from here you can just calculate for K, which is just going to be 40 times 50 times 10 to the power minus 3 divided by 20. So this K is going to be equal to, I think you will get how much? I think you'll get 0.1 from here, okay, because this is going to give you 2, this is going to give you 2 and 50 would give you 100 multiplied by this 10 to the power minus 3 is going to give you 0.1. That's it. So this is going to be 0.1 watt per meter Kelvin. That's the thermal conductivity of wood. So just for reference, you can see that the thermal conductivity of glass is around 1.4 watt per meter Kelvin. You can see that thermal conductivity of wood is 10 times less than thermal conductivity of glass, which means with respect to glass, wood is a bad, conductor. With respect to glass, I am saying wood is a bad conductor of heat. Glass is a better conductor, I would say, because its thermal conductivity is higher. And as you saw, air has got a thermal conductivity of 0.024, which is even 10 times less than that of wood. So it is, you can say it's a worse conductor of heat with respect to, glass and wood. So if you say that if you have glass, okay, if you have glass, if you have wood, and if you have air, if you have these three materials, then glass, has got the highest value of K, and air has got the lowest value of K. So if you want to see in the increasing, sense of heat transfer, this is the increasing sense. Glass would, readily transmit heat. Air, on the other hand, is a bad, it's a bad conductor of heat basically. Okay, because it has a lower value of K. Okay, wood is intermediate because its value is around 0.1 watt per meter Kelvin. Okay, all right. That's a simple problem. I guess that's the same Fourier law that I'm applying. Now we'll solve a very interesting problem. And I'll say what basically this problem is trying us to evaluate, or it's saying, or what this problem says is something that I'll discuss. But before that, once again, if you have any doubts, you can ask me, and if not, we will look this problem. Okay, so what this problem is asking us to evaluate is that they're asking us the same. They're saying that given that let's say I have a slab, okay, let's say I have a slab of this form. Let's draw it in the form of a slab for you to understand in a better way. Okay, now what they're saying is I have a slab whose thermal conductivity now is a function of space. Okay, so there are some materials where indeed your thermal conductivity varies along the spatial direction, and this is one such space. This is one case of such materials where your thermal conductivity, instead of it being constant, it is actually a function of space, and it has basically got the form that your K is equal to Ax plus B. which means you can see that if you move in the direction of increasing x, your thermal conductivity is essentially increasing if your A and B, the constants, these are greater than 0. In that scenario, if you move along the plus x direction, your thermal conductivity of this slab, of this facial kind of slab, is essentially increasing. Okay, this is now a different scenario, and we will see that we will exactly, and will precisely see that now you cannot say that your dt dx is going to be constant. That is, your temperature profile will now no longer be linear. Okay, and you must appreciate that you can use the fact that your temperature profile dt dx is just T1 minus T2 by L only when your thermal conductivity is constant. And if your thermal conductivity is not constant, as we will see through this example, you cannot say that your dt dx is linear, and we will prove this in this case study. Okay, so so the objective, as I said, the objective of this problem is considering the fact that your thermal conductivity is now a function of x, which is of this from some, so as you can see, it's a linear function of x, where these constants A and B are some arbitrary constant with magnitudes greater than 0. Our objective is to find dt dx, and then the temperature profile in this scenario. And here also we will see that the temperature profile will no longer be linear because your thermal conductivity is now not constant, and it is just a function of x. Okay, so I call this problem a variable thermal conductivity problem, and we will see how we'll evaluate the temperature profile in this case. Okay, but anyways, first come first, since we are still invoking, but still you need to understand that we can still use the fact that my heat transfer is one dimensional. That means I have that means the direction of heat transfer, okay, is just along x. And if it is just along x, I can still use the simplified version of Fourier's law, which says that my qx, or the flux, at least I would say, is equal to now k, but this time this k is a function of x times dt dx. See, this form is still applicable because my heat transfer is still one dimensional. Okay, I'll write here down that heat transfer is still one dimensional. The only thing that has changed is that the thermal conductivity of it being a constant, it has now become a function of space, and it just varies linearly with space. Okay, that is what the problem is saying us. All right, but they have given us an important information. They have said that the heat flux in this scenario where your thermal conductivity is varying with space, the heat flux is constant. That is something that they have said to us. Okay, so we will say that this heat flux is constant, and without the loss of generality, will denote this constant as what? As some, let's say, C. Okay, so in that scenario, my dt dx would be minus C times q of x, and this C is a constant because they have already said that the heat flux is a constant, and q of x is ax plus b. That's it. That's your that's your dt dx. Okay, but the more interesting point is that how do we now get the temperature? So in order to get the temperature, what I will do is I will take the dx onto that side, and it just becomes minus C times ax plus b times dx. Okay, and now we'll do some, and basically now we'll use the concept of integration. We are using the concept of integration because, please pay closer look here. Okay, now since I know that my thermal conductivity is essentially increasing along the positive x direction, because I have assumed that my A and B's are greater than 0, this means that my temperature profile, and also the rate of heat transfer, they will essentially change when I move in the plus x direction. Which means I can no longer say that my rate of heat transfer is going to be, the temperature from this phase minus the temperature from this phase divided by delta x. Because at each and every x, since your thermal conductivity is changing, your rate of heat transfer will change even though your flux is constant. Okay, and that change is attributed to the change in thermal conductivity. So what we will do is, In order to tackle this problem, we will choose a small, strip. Okay, we'll choose a small strip at some, let's say, generic x, and the width, the width of this small strip, we will call it as dx. Okay. So then what we will do is, we know, sorry. So what do we know? Okay, let's not write this form. Let's use this form that we use. So what we know is, we know that at any particular, at any particular location x, we know that dt dx is equal to minus c ax plus b. Okay. So what we'll do is, we'll integrate this with respect to x. Okay. And from where do we need to integrate it? Because so first of all, why are we integrating it? We are integrating it because we know that the rate of heat transfer is going to change with x. Please keep in mind that although the heat flux is constant, your rate of heat transfer will change with space, because your thermal conductivity is essentially changing with space, basically. Okay. So or at least if you speak in terms of the temperature, your temperature will basically vary with space. Okay, that is something that that you need to understand. So what we'll do is, at any generic x, okay, we will pick, we will basically calculate what is dt dx, and then integrate it from the length x equal to 0 to, let's say, x equal to L. That's the idea that we will do. Okay. So when I integrate it, this just becomes t of x. Because c is a constant, this c will come out of the integral, and this just becomes dx by ax plus b, and we know that this integral will just give you ln of ax plus b. Okay, that's what this integration would give you. So now you know that t of x is equal to minus c. Okay, there will also be a constant because we are doing an indirect integration. So this t of x will now be minus c times ln of ax plus b plus a constant. Okay. Now, how do we evaluate this constant? That's easy, because we know that at x equal to 0, that is for this phase, my temperature is T1. So we'll substitute this information, that is known as the boundary condition. So at x equals to 0, I know that my temperature at x equal to 0 is T1. So this means that T1 is equal to minus C ln B plus constant. So your constant then comes out to be equal to T1 plus C ln B, where C is known because they have said that the heat flux is just constant. Okay. And then if you substitute the value of this constant here, you just need to substitute the value of this constant. You will eventually get that your temperature profile T of x is going to be minus C ln of ax plus b plus T1 plus C ln B. And if you kind of, simplify this or rearrange this, you will get T1 plus C ln B by ax plus b. Okay, that is precisely how your temperature variation that is precisely how your temperature will vary along the x direction. Oops. See, the important takeaway, anyways, let's not make any boxes here. Let's like this. Okay. See, the important takeaway is that although your heat flux was constant, okay, you can argue that since your rate of heat transfer is this heat flux times your area, the rate of heat transfer might be constant, okay, but your temperature will no longer vary linearly with x. And that's the reason why at each and every x, okay, your temperature will not vary linearly, and that's why what we did is we took a small strip, we calculated what is the dt dx of that strip, and then integrated it from 0 to L to basically get the temperature variation along the length of this slab. And all this, fiasco came because of the fact that your thermal conductivity is a function of x. Okay, so you can see that even though your heat transfer is one dimensional, if your thermal conductivity is a function of x, then then you can say that your temperature distribution is not linear, and now you can say that it's a complicated distribution. It's a logarithmic distribution that you can see here. Okay. All right. Uh, so that's the idea behind this problem. And yes, we have solved for the temperature difference. That's the answer. Is the So this is how the temperature profile would look like. Okay, and that's it. All right, I'll stop here again for some couple of minutes, and then we'll discuss one more problem, before calling it a day, and we'll discuss this problem. And in this problem, we'll learn about the other two modes of heat transfer, which is convection and radiation. And before before going into the details of this problem, I will quickly discuss what is convection and what is radiation heat transfer. Okay, but before that, if you have any doubts on the previous problem that we solved, please let me know. Please let me know. Okay, all right. Okay, now as I said, before proceeding into the next problem, let's look into the other two modes of heat transfer, because till now we have seen uh, conduction. This we have already seen. We have seen the Fourier's law. But now we'll be looking into the other two modes of heat transfer, convection and radiation. So broadly speaking, if I speak about conduction, it means, so the conduction heat transfer primarily comes into play when the material medium is not moving. Let's say I am trying to analyze the heat transfer for a slab which is at a temperature T1, and the other phase is at a temperature T2, but the material of this slab, which is shown by this hatched area, it is not moving. So then how does heat transfer actually takes place? So what basically happens is that, so there are molecules, as you know, these materials are made of molecules. So there are molecules which are stacked in between, the faces of this place. And how heat transfer takes place is that, so the molecules gets a little bit displaced from their equilibrium position, and basically this leads to molecular motion, basically vibration, to be precise, which transmits the disturbances forward, and this is how heat transfer takes place. So this mechanism is known as diffusion. Okay, so diffusion is the mechanism through which heat transfer takes place in conduction. However, if let's say now I have a scenario where, let's say, I have a flat plate, okay, maintained at some temperature T1, and now I have a fan, you know which is kind of blowing. So let's say this fan is rotating with some angular velocity omega, and this is blowing air over over this flat plate, and the air have a temperature T infinity, and let's say T infinity is less than T1. So then what happens? The first and foremost thing that you need to understand is that now there is a bulk motion of this air, and it is not just confined to diffusion where there is vibration of molecule. Yes, I understand there is diffusion here. There is diffusion here because when the air moves forward, still the molecules vibrate within their space, right? So there is diffusion, but there is one more phenomena that is taking place, because through an agent, I have displaced the bulk volume of air, and this is known as bulk motion. Okay, so the combined effect on heat transfer because of bulk motion and diffusion is known as convection. Okay, but however, if I only focus on the bulk motion of heat transfer alone and disregard the diffusion, then this is known as advection. Okay, I repeat, if I speak about the combined effect of the bulk motion of air and the diffusion aspect, because the molecules are still vibrating whenever I am moving that bulk chunk of air, the combined effect of this bulk motion and diffusion is known as convection. If I consider the bulk motion itself, that particular aspect only is known as is what is known as advection. So in other words, you can say that convection is basically diffusion, which you can also say conduction, because conduction heat transfer takes place primarily by diffusion plus advection. So sometimes in the literature, people interchangeably use advection and convection to be the same, but they are not essentially the same. The mechanism is different. So advection is convection minus the diffusion part or the conduction part. Okay, so that is known as conduction. So now we have known convection, which is primarily by diffusion. We have seen convection, which is diffusion plus the bulk transport, which is nothing but advection. So advection plus diffusion is convection. And, and at the last, we have radiation. So please understand that unlike conduction and convection, okay, radiation doesn't require the presence of a material medium. Just like conduction requires a solid medium or a gaseous or a liquid where the medium is stationary, and if there is just diffusion, then we have conduction. If there is a bulk motion plus diffusion, we have convection. While on the other hand, radiation doesn't, so for radiation heat transfer to take place, it doesn't require a material medium in to intervene basically. For instance, the energy that we receive from the sun and the energy that the earth get to heat up, that our earth gets to heat up, is the energy that comes from the sun. That mechanism takes place by radiation. Okay, so just so I hope the fundamental difference between conduction, convection, and radiation is clear to you guys. Okay, so just one more thing. So just like how you use the Fourier's law to evaluate the rate of heat transfer in conduction, there is something which is known as Newton's law of cooling. For instance, if you ask me that what will be the rate of heat transfer that will take place from this heated plate to the air that is flowing with which possesses a temperature T infinity, then my answer would be the rate of heat transfer, which we'll call it as Q convection, is going to be H, we'll see what H is, times the area. This area now is called as the frontal area of this plate, which means the area of the plate which is exposed to the air is the area that we will calculate for evaluating the rate of heat transfer by convection. And this area is known as frontal area, or you can say that this is the area that is exposed to the air that is flowing atop the plate times the temperature difference. Okay, this, which is nothing but T1 minus T infinity. This is primarily the rate of heat transfer for convection, and this, you can say, this formula that I wrote, this is known as Newton's law of cooling. So what Newton's law of cooling says that whenever there is a bulk fluid that is flowing plus there is diffusion that is taking place, that or in other words there is convection, the rate of heat transfer due to convection is proportional to the frontal area, it is proportional to the temperature difference. To eliminate the proportionality sign, people use this H. This H is known as the heat transfer coefficient, and this heat transfer coefficient has got an unit of watt per meter square Kelvin. That is obvious because this unit is watt. The area has got a unit of meter square. This has got a unit of Kelvin or degree Celsius because this is different. So H will naturally have a unit of watt divided by meter square times Kelvin. and that's the unit of heat transfer. Similarly, in the same spirit, okay, in the same spirit, you can show that, I mean, I'll not primarily derive this, but you can show that your heat transfer due to radiation is equal to epsilon, we'll see what epsilon is, times the area, this area remains the same, that is the same frontal area, times T1 raised to the power 4 minus T2 raised to the power 4, where T1 and T2 are the two, where T1 and T2 are the two bodies whose surfaces are exposed to temperature T1 and T2, in between whose we are trying to calculate what is the radiation heat transfer. Okay, and this epsilon, okay, and in fact we should say that this is the net radiation, so this is actually the radiation heat transfer taking place from body 1 to body 2, and this epsilon is known as emissivity. Okay, and this is actually a property of the bodies. Okay, so if we know emissivity, for instance, if we want to calculate what is the radiation heat transfer taking place from the earth with respect to the sun, okay, or in the other way around, like from the sun to the earth, whatever you calculate, you need to know the emissivity, you need to know the area, plus you need to know the at least the temperature difference that is there on the surface of the earth to that on the surface of the sun, basically. Okay, and this is primarily heat transfer due to radiation. Okay, and this form, okay, this form, this epsilon a times T1 to the power 4 minus T2 to the power 4, there is a law. So we'll not dwell much onto this thing now, because we'll solely be focusing on this when we'll learn radiation heat transfer. But just to give you a heads up, there is something which is known as Stephen-Boltzmann law, and this form actually comes from something which is known as Stephen-Boltzmann law. And there are a lot of other things that we will see. So basically, there is something which is known as black bodies. This is actually true. So for black bodies, this emissivity is actually equal to 1. But for non-black bodies, we'll have a we'll have a non-unit emissivity, and all those things we will see when we learn radiation. There is also something which is known as gray bodies. Then all those things, all those concepts, there is something which is known as view factor, and all those things we will see in details, will in depth when we will study radiation heat transfer. But rest assured, this is one form of calculating rate of heat transfer whenever there is radiation taking place. Okay. All right. So again, the bottom line is that whenever you have conduction, your rate of heat transfer is given by this. Whenever you have radiation, this is how your rate of heat transfer will be. For instance, if you want to calculate the radiation heat transfer in this scenario, then your T2 will just be equal to T infinity. That's it. T1 to the power 4 minus T infinity to the power 4. That is the heat loss due to radiation. Okay. But try to understand that whenever this temperature difference is not very appreciably different, radiation, the heat transfer due to radiation is neglected, because you see that, there is fourth power of this temperature. Okay, you can prove that if T1 minus T2 is very much less than 1, or not 1, maybe 1 is, if I say it's 1, it's incorrect. If I say that if T1 minus T2 is not appreciable, meaning that if there is not vast difference of temperature in between the two bodies, then convection will overpower radiation, because the difference come in the fourth power in case of radiation. But if this difference is too large, for in fact, for example, the temperature on the sun's surface with respect to the temperature on the earth's surface, there is a vast difference in temperature. In that context, will your and of course we also don't have a material medium. So then the only method, or the only possible way of heat transfer is just radiation. So we'll just have radiation solely dominating into the picture. But if, let's say, there is convection and radiation taking place, and if the temperature differences are not that much, convection will inevitably dominate over radiation. So this is something else that also you need to understand. And these are kind of things that you will see when you solve problems, and when you solve problems at your own. And through practice, you can of course appreciate and observe these kind of things whenever you solve. Okay, so so that's the idea uh, behind convection and radiation heat transfer. I'll again stop here for a couple of minutes. If you have any doubts, you can ask me. There is a problem, but again, this problem will not solve it today, because we don't have that much amount of time to solve this problem. Instead, uh, let's just try to build upon this concept that we just saw. And of course, this concept. So if you know the concept, problem solving in heat transfer is very easy. Okay, but provided you need to have a crystal clear information on the formulas that you are writing, and it's just not like mugging up the formulas. You just need to know that how the formula basically comes. For instance, we saw that how the simplified form of the Fourier's law come from the generalized uh, Fourier law, okay, for conduction. And similarly, the same holds good. We will see that for convection and radiation as well. But since this course is just for conduction and radiation, we will not go in details into convection heat transfer. There is a separate course in NPTEL which deals in convection. I think the name of the course is Fundamentals of Convection Heat Transfer. And if you are interested, you can check that course. And there, there will be in detail analysis, or there will be a detailed analysis of convection. Okay. There is something which is known as boundary layer analysis, and all those things we'll do. There is something which is known as thermal boundary layer in flat plates, and all those things. So there you'll be learning convection in details. Okay. But in this course, we'll be sticking primarily to conduction and radiation heat transfer. Okay, so that's the let's end here for today. I mean, let's end the discussions here for today. You can ask your doubts, but what we learned is we solved certain important aspects. We looked into, first of all, we looked into the Fourier's law. Then we looked into two important assumptions: the assumption of 1D heat transfer and the thermal conductivity being constant, which leads to the simplification of Fourier's law to be just k times dt dx. We solved certain problems on this, and then we looked into a problem where we saw that putting air in between glass panes reduces the rate of heat transfer. And then we looked into another problem where we were asked to just calculate the thermal conductivity of wood. And then we looked into a different problem, which I feel this is an important problem, because we saw that even if even if we had 1D heat transfer, your temperature profile was not linear because your thermal conductivity was varying along space. Okay. And then we saw that in fact that instead of temperature profile being linear, which I said, since your thermal conductivity was varying along space, you saw that your temperature was no longer linear. Temperature profile was not linear. Instead, it was logarithmic in nature. And then we ended this discussion by looking into the three fundamental concepts of conduction, convection, radiation, and how we calculate the radiation heat transfer, the convection heat transfer, and radiation heat transfer. And also we looked into the essential difference between advection and convection, and we said that advection plus diffusion essentially, the cumulative effect of advection and diffusion leads to convection. Okay. All right. All right. So that's all that we saw today. I I hope we'll meet. So I hope you will have many more participants in the next week. Please join these sessions because this gives you a flavor of how you need to tackle your assignment problems, and inevitably they are going to be helpful to you. So please join these sessions, and yeah, so we'll meet in the next week at the same time, 3 to 5 p.m. using the same link on next Saturday. Uh, till then, please, till then, I hope you enjoyed this session. I hope you are liking this course. Please share, as I say, please share your doubts in the discussion forum, and we'll meet next week, the same timing, using the same link. Thank you very much. We'll see you all in the next week.